Auzubillahiminash-shaytanir-rajeem. Bismillahir-rahmanir-rahim. Assalamu alaikum class. How are you all? Alhamdulillah, I'm fine and hope that you all will be fine. Okay, today we will discuss the numericals of the chapter that has been completed on the last video lecture, and it has also been discussed. The last chapter has also been discussed in the Zoom session. Today we will, inshallah, apply these theories to numerical problems. In the first numerical, that is, find the radiation resistance of Hertzian dipole of length lambda by 40, lambda by 60, and lambda by 80. We have to, in this question, we have to find the radiation resistance of Hertzian dipole or alternate current element that was defined as the reference or the ideal dipole element. We have to find the radiation resistance for these parameters. That is the length, which is given in different for three parts. The formula for the radiation resistance of Hertzian dipole is RR 80 pi square dl over lambda. That is the standard formula which has been described in the last lecture. 80 pi square is the constant, dl over lambda is given, that is lambda by 40, and 1 by lambda, sorry, dl by lambda. Dl is first, in the first we have dl which is lambda by 40. Here we put lambda by 40 divided by the lambda. As we solved it or simplified, we got radiation resistance as 0.493 ohms, that is for lambda by 40 length. The second is the lambda by 60. The length of lambda by 60 is used in the same formula, that is 80 pi square. In this formula we will put lambda by 60 and simplify it. We got 0.219 radiation resistance using the same formula. And the third part, that is lambda by 80, we are using the same formula, that is dl is lambda by 80 divided by lambda. We got 0.123 ohms. It will also be noted that as we increase the length, as we decrease the length, sorry, as we decrease the length, radiation resistance also decreases. So that is being noted that in Hertzian dipole, the length is being decreased, the resistance of the radiation has also been decreased. Okay, another question we will discuss, that is, in this question we have to find the directivity of a current element IDL. Uh, find the directivity of the current element. That we have to find the directivity of the current element, that is, we have to derive the directivity of the current element. As we know that for the Hertzian dipole, E is equals to I dl sine theta over 4 pi epsilon naught multiplied by omega over r v naught square. That is the electric field equation for the Hertzian dipole. As we simplify the equation, it will give us 2 pi f, as it is being replaced by omega. I dl sine theta 4 pi epsilon naught r. We know that v naught is equals to 1 over mu naught of epsilon naught. We replace it v naught into 1 over mu naught into epsilon naught. There is a under root with the v naught value. So if we square it, the under root, the square root is being resolved, been cancelled out. So we got 1 over omega of epsilon naught into mu naught. Further, we simplify the formula. It becomes ideal sine theta 2r into f. That equation 2 pi f ideal sine theta over 4 pi epsilon naught r 1 over mu naught epsilon naught is being simplified here. After simplifying, we got this equation, that is ideal sine theta QR into F under root mu naught epsilon naught multiplied by under root mu naught epsilon naught over epsilon naught. As we know that mu naught over epsilon naught is equals to n naught and v naught over f is equal to lambda. So we replace this mu naught over epsilon naught by n naught, and this f is being replaced by v naught over lambda. So after simplifying, we got E is equal to 60I dl sine theta over lambda r. By putting the values this and this one in this equation, but we know that the maximum radiation for Hertzian dipole is occur at pi by 2. We replace theta by pi by 2. Sin pi by 2 is 1. Becomes 60I dl over lambda r. That is the E maximum for alternate current element or Hertzian dipole. In the last lecture, we have viewed the radiated power of the current element. Alternate current element is this. If we assume that the radiation power, we know that if the radiated power should be, if we assume that the radiated power should be 1, then this equation becomes for I, it becomes this. If we simplify this, in this equation, if you put the value of I, if you put this value I in this equation, E maximum becomes 60 over R under root 80 volt per meter. Then the E max becomes 60 over R under root 80 volt per meter. We know that radiation intensity is equals to RE square over N naught. Last time it has been discussed in the last lecture. If you put N naught value, that is 120 pi, and simplify Ri by putting 120 pi against N naught, Ri becomes 3 over 8 pi. The value of Ri or radiation intensity becomes 3 over 8 pi for Hertzian dipole or alternate current element. In the last lecture, it has also been discussed that directive gain is equals to 4 pi Ri over PR. We have Ri that is 3 over 8 pi. We put the value of 4 Ri that is 3 over 8 pi, that is 4 pi multiplied by 3 over 8 pi divided by PR, and we have taken the PR as 1. The formula that becomes after simplifying is 3 by 2. Pi has been cancelled out. 4 1 are 4, 4 2 that it becomes 3 by 2, that is 1.5. So the directivity of alternate current element is 1.5, that is GT is 1.5, GT maximum is 1.5. Add received power that is taken as 1 watt. If we convert it to decibel, it becomes 1.70 dB. It becomes 1.70 dB. So here we have, in this question, we have used the formulas that have been uh, discussed in the last chapter for Hertzian dipole and find the directivity of current element that has already been derived. We have just proved it here by putting some assumptions and some constants. Okay, going forward to the next question, that is find the directivity of a half-wave dipole. Here we have to find the directivity of a half-wave dipole. We know that the half-wave dipole electric field maximum value is 60 I over R. Here we know that E maximum for directivity for E maximum for half-wave dipole is 60 pi over R. We know that the directivity of a half-wave dipole is 60 pi over R. That is, sorry, the maximum value of electric field is 60 pi I over R, and radiated power is 73 I square, but we have to find it for 1 volt that we have done in the last question. So by putting the PR, that is 1 volt, I square 73 I square will become I PR is equals to 1 is equals to 73 I square. I become 1 over root 73. If you put this I value in this E maximum, it becomes 60 over R multiplied by 1 over root 73. We know that the GT maximum is 4 pi Ri over PR. 4 pi Ri over PR in here PR is 1 volt, so it becomes 4 pi Ri. We know that the value of Ri is R squared E square over N naught. That is the general equation for Ri that has been discussed so many times in the last chapter and again uh, in a minute before, that Ri is equals to R squared E square over N naught. If we simplify it by putting the value of E maximum, that is 60 over R and multiply 1 over root 73, that is here 4 pi R square over N naught multiply by E, that is we have 60 over R into 1 over root 73. After simplifying, it becomes 1.644. That means the directivity or the GT maximum for the half wave dipole for 1 watt radiated power is 1.644. That is basically the generalized GD for every half wave dipole antenna, and it has been used further in the antenna calculations. Please note that these values which are derived as a constant will be used for all of the same configuration antennas. That is for that we have in problem 3.2, as we have derived GD maximum for alternate current element, and it will be standard used for all alternate current elements. And here we will drive it for half wave dipole, then it has to be used for all of the half wave dipole configurations. Okay, moving on to the next problem, that is an antenna whose radiation resistance is 300 ohms, operate at a frequency of 1 gigahertz and with a current of 3 amperes. Find the radiated power. Here we have to find the radiated power. Antenna radiation resistance is 300 ohms, that is RR. Frequency also given at which the antenna is being operating, that is 1 gigahertz. Okay, here we know that the radiated power is equal to I square RR. We have I, that is 3 amperes, which is given in the question, and RR RR is also given, that is radiated radiation resistance, that is 300 ohms. So we got the radiated power, that is 2700 watts. That is too much for the antenna. Now, the next question is the effective area of a half-wave dipole operating at 500 megahertz. Okay. Find the what is the effective area? We have to find the effective area in this question for half-wave dipole that is operating at 500 megahertz. Okay. Okay. The effective area formula is lambda square over 4 pi GD for half-wave dipole. Here we have the frequency that is given, which is 500 megahertz. We put all of the values in the formula. Here we first find the lambda. First we will find the lambda, that is lambda is equal to c by f, that is c the velocity of the light divided by the frequency that at which the antenna is operating. We got the lambda, that is wavelength, that is 0.6 meters. Then we have the formula, that is lambda square over 4 by GD. We know that in the last question we have derived the GD, that is for half-wave dipole, which is 1.644. We put all of the values including lambda that has been derived a bit ago is being used in the effective area formula. We put all the values and we got effective area, that is 0.047 meter square. In the next question, we have to find the effective area of Argent dipole operating at 100 megahertz. Here we have to find the effective area of the Hertzian dipole that is operating at 100 megahertz. First, we have to find the wavelength, that is c by f, which is the speed of light divided by the frequency at which the antenna is operating. We know that in the last question we have derived the Hertzian dipole directly, that is 1.5. We have the effective area formula, that is lambda square over 4 pi. Lambda square over 4 pi GD. Lambda square we have is 3. We have to square it, multiply by GD, that is 1.5, which has been derived a bit ago. And the 4 pi is the constant. After including the ingredients in the formula, we got the effective area, that is 1.07 meters square. So here we have find the effective area of the adjacent dipole. We have find the effective area of half-wave dipole. Here we find the radiation power of the antenna, which parameter have been given. And we have derived the directivity of half-wave dipole. Here we have derived the directivity of alternate current element. So these were the questions that have been selected from the last chapter of the topics that has to be discussed, and they are discussed. So we are moving on with another topic, that is from now we are starting a new chapter, that is analysis of linear array. The first topic of this chapter is array antenna. We will discuss the analysis of linear array, in which the first topic is array antenna. Okay, in the array antenna, in some situations, gain of a single antenna element is not sufficient. Definitely, one element does not provide us the maximum power, desired power. So we have to add some elements, more than one elements. More than one antenna element connected is called array antenna. Yes, we have to. If we have to increase the gain of the antenna, we have to increase the elements in the antenna. Increase the gain, that has been described, that every element has its gain, and after all of the element gain has been sum up and give us a big gain, like the cascaded amplifiers. Extremely useful in airborne as well as in ground based applications. Okay, so that is the array antenna. Array antenna is basically nothing, just number of elements uh, connected with each other to give you the maximum gain, like the cascaded amplifier. And the application is airborne as well as in ground-based applications. Now, further we will discuss the directional characteristics of dipole, that is radiation pattern of antenna. and other characteristics. Okay, directional characteristics are also called the radiation pattern of antenna. They are observed in free space as disturbances at different angles. They can be analyzed by graphical representation in two ways, that is field strength pattern and power pattern. These both representations are the same as was discussed in the last chapter in antenna characteristics. Pattern are of two types, that is horizontal and vertical. Horizontal pattern is represented in 90-degree angle and vertically represented as where the phi is constant. Sometimes the pattern has been shown as electric and magnetic field planes. Electric and magnetic field planes, if the pattern is perpendicular to the E field, the pattern will be termed as electric field plane, and if the pattern is parallel to magnetic field, it is known as magnetic plane. These both planes are called the principal planes. Moving further, we will discuss the radiation pattern of an AC element expressions. Alternate current element expression. Expression means the formula for alternate current elements. We know that electric field intensity for alternate current element is 60 pi IDL over lambda r sin theta. That has been discussed in the last chapter also. That is defined as the radiation field of Z directed current element. This equation is defined as for Z directed current element and the unit is volt per meter. Next is the radiation pattern expression, that is equation of center field vertical dipole of finite length. That means here we will discuss the expression for the vertical dipole which has some finite length, but it has been fed from the center, that is the source is being coupled with the vertical dipole in the at the center of the antenna. We have electric field, that is normalized electric field, which is equals to 60 Im over r multiplied by cos beta L cos theta by 2 minus cos beta L by 2 divided by sin theta. En means normalize. Here the length, if we put the length is lambda by 4, the formula become cos pi by 2 cos theta divided by sin theta. In this formula we have put lambda by 4, that has been squeezed to this equation, and that defines the normalized electric field. Next is the two element uniform array. As it has been discussed that the arrays are nothing but the elements that are connected with each other to make an antenna. That is the system of antenna. It can either be similar or non-similar with each other. That means the elements have the if the elements have similar properties, then it becomes a uniform array. If they have non-similar properties with each other, or the elements that have non-similar properties with each other and connected in an antenna, then it will be a non-uniform array. As we are talking in the sense of uniform array, then we will discuss the similar property elements that are connected with each other in order to increase the directivity or gain of the antenna. Radiation pattern of two element array is expressed as 2 Ea cos pi d cos phi over lambda plus alpha E by 2. Here d is the spacing between the elements. Phi is the angle between axis of array and observer. and alpha E is the excitation phase. Here defined in the figure. Here's the figure that defines the two array, that point is the A and the other point is the B. These are the two element arrays, two elements that are connected to make an array antenna. This is the observer, or the we can say that the receiver. The line that is observed from A to the observer is called ray A, and the line that is between the element B and the observer is called ray B. The angle with the horizontal axis is called phi, and the arrows which are going upward are called the current amplitudes. D is the distance between the array elements. In practical application, more than two elements are used. That means there is no such gain is observed in the two elements, so it is not practically used. That is two elements. More than two elements are used, and the examples are there. Because if we use two elements, there is no such gain observed. That's why it's not practically used. Then there is uniform linear array. Uniform linear array is an array antenna that is the combination of elements spaced and excited equally along a straight line. That is, their excitation and their space between the elements is constant. That's why they are called linear. I repeat again, uniform array is called linear when there is a constant spacing between the elements and they are excited equally. It produces narrow radiation beam, which is very good for the receiving or the transmission. Highly recommended for point-to-point communication. An application is radar. Here we have discussed in the picture uniform linear array, that is nth uniform linear array. Here nth uniform linear array has been observed. Four arrays have been used to define the system. Again, here is the observer, that is P, that 1, 2, 3, 4 defines the four elements going up to nth elements. The spacing is same. The theta that is making with the observer is same, that is d cos phi, and phi is the angle from the horizontal to the observer ray to the element. The formula for electric field is sine n psi by 2 divided by sine psi by 2. That is the electric field for nth arrays. Their features are: the normalized electric field is the combination of radiated electric field divided by the electric field of the first element, and is equal to n. Maximum value occurs at psi is equals to 0, that is called principal maxima. Minimum value occurs at n psi over 2, which is equal to plus minus k pi, and k are the elements from 1 to n. The minimum value is also called the the minimum value is called the principal minima. Here is the picture defined. This is the main loop, that is the big one at the center, and is called the main beam. The other sides are called the side loop level or the side loop level, SLL. The first side loop label after the main beam from left in the left and in the right both are called the first side loop labels, that is FSLL, and other are only called side loops. The distance between two side loops at the horizontal is called null, and from the first side loop starting to the first side loop ending at the horizontal is called the first null. This diagram is basically constructed over E and phi, that is E at the horizontal and phi at the vertical axis. First secondary maxima loop is called first SLL, that is defined here, this one or this one. Amplifier difference, angular difference between FSLL and main beam is SLR, that is side loop ratio. There is a difference between main beam and the first side loop is called side loop ratio. Null of main beam angular difference is null to null beam width. Main beam nulls provide you the null to null beam width, that is the width of the main beam, and the 3 dB bandwidth of 3 dB bandwidth, sorry, 3 dB beam width of main beam is called HPBW, that is 3 dB beam width of main beam is called HPBW, that is half power beam width. These are the features of the uniform linear array. Remember that we are talking about the uniform linear array of non-directional antenna, but the properties are linear, that is the difference between the element distance and excitation are same between the elements. First side loop level ratio is equals to first side loop level divided by main side loop level, that is this one. The ratio between this and this, either this or this, left or right first loop with main beam, is called side loop ratio, and it is measured in dB. For uniform array, side loop ratio is approximately minus 13.5 dB. That is standard and is calculated universally. Now we will discuss further two type of array antennas, that is broadside array and endfire array. Broadside array antenna is referred as broadside because the maximum radiation occurs perpendicular to the axis of array. That means the maximum radiation at broadside array will occur perpendicular to axis of array. That means any array antenna that has a maximum radiation along perpendicular axis is called broadside array. And the second is endfire array. In endfire array, maximum radiation occurs parallel to the axis of array. That means any array antenna which has the maximum radiation occurs parallel to the axis at which, or parallel to the horizontal axis at which the antenna is being coupled, is called end-fire array. The beam width of both of the type of arrays is given, that is for broadside it is 2 lambda by nd, and for end-fire it is 2 under root 2 lambda by nd. Nd is the length of the array. I think that is quite enough for today lecture. Inshallah, we will discuss further things in the next lecture. Thank you very much. Inshallah, we will discuss more things in the later lecture. Thank you.